Again, welcome to part one of this discussion for basically chapter. Let me make sure I have my pen working. Okay, basically that we're going to be discussing chapter 19. So basically, to set it up correctly, we want to understand the concept of the energy and how we impact the energy of a gas. So here is a scenario. I have a gas in here. Doing my best in drawing it in here. Okay. So imagine with me that this is a gas, okay? And the gas is contained in this. Obviously, we need to close it from all ends, at least to know its volume. So what I can do in here is I can have this top of the gas, which is, I need to draw a line, man. It needs to be a straight line. I'm sorry about the drawing in here. Anyway, so this is a line. Think of it as like a piston, where the piston can go up and down to allow me to change the volume. So the cross section of the piston is A, the height of the gas is H. So there is a gas in here contained in this space in here, okay? This is an attempt to draw the particles of the gas that are in random motion in here, which gives rise to the concept of temperature. So imagine that we have a thermometer that can measure that temperature. We know the volume from this expression, which is just the cross-section times the height h. I'm assuming that this is h, okay? And also I know the if I can have a gauge in here to measure the pressure for me, P, then I can simply say that if this is an ideal gas, namely the density is not too high, that allows for collisions between the particles. Go back to the previous chapter. So we know PV equal to nRT. Okay, we have a gas that is well defined in a PV diagram. So this is how this gas would look like. So it has a specific point. This is volume. This is the pressure. So in this point, for example, of that volume, AH, so this is the volume, this expression. This is the pressure that the gauge has measured for me. I know the temperature exactly for this gas. It's equal to, given by this PV divided by nRT. So we know all the state of this gas. We want to change its energy though, meaning its temperature. Okay, remember the previous chapter? The temperature for a monoatomic gas, for any kind of gas, is proportional to the temperature, because the kinetic energy of individual particles is proportional to the temperature. In case of translation itself, it's 3/2 of RT, or 3/2 of kBT, I'm sorry, for the particular points, for the particular particles, namely for the dots themselves, where kB was Boltzmann constant. Anyway, and we were able to recover R from there. So one way of doing actually increasing the temperature is to put it under a on top of a stove and turn the heat on. So you could add heat to it. Okay. So one way for the energy to change, this is the amount of change for the energy, is simply to add heat. The symbol for heat is the letter Q. Okay. So we could do that. Just add heat to it and you're fine. So you could change its energy. Another way of actually doing it, provided that the volume doesn't change. If the volume changes, if the gas expands, actually it's going to do work against the environment, so we expect the energy to change also. So another way actually of changing the energy of the system is having the system do work against the environment by having it expand. Or if we compress it, actually it's the other way around. We're having the work done from the environment to the system. So where in the world that work is going to go? It's going to go to the energy of the system. So that's also another way of changing the energy of a system. So let's consider the second scenario now, namely that really we don't have now a heat source. In other words, we don't have that furnace. So this is again my gas. This is the piston that can move up and down. And for the sake of argument, what I'm going to do now, so there is no heat source now. So the only thing that we can do is move the piston up and down. Okay. So actually we're going to move it down now. So if the piston is moving down, so at some point the height of the gas will change from the current height h, which is this entire height, down by an amount which is dx. So the volume will change now by an amount which is equal to the area A that did not change times the change in height. Obviously, if I do it this way, if I'm compressing the gas, dV is actually negative. Okay, the gas is the volume is becoming less and less, so the change in volume is going to be negative. So what's going on in here? If for me to move it, I really have to fight this force that results from the pressure in here. So there is a pressure in here exerted by the gas on all the sides of the container, including this specific one in here. So there is a pressure, and remember from physics 1, pressure is just the force divided by the area, which means that the force in here I need to fight is the pressure times area. So that's basically the force I have to vanquish. That's the force I have to defy if I want to do this actual thing, namely compress the gas. Okay, so the force is clearly pointing upward in here, and the work that this force basically will be forced to do in this case is force times displacement. So the amount of work that is going to be needed to do this is going to be force times displacement. But the force is upward, the displacement is downward, so I really need a negative sign in here, minus the force, which is PA, times the displacement, which is dx. Okay, and again, this is the force, which is just coming from the pressure times the area. This PA dx is nothing but the change in volume. So another way of writing this expression is minus P dV. Okay, let's think about this expression for a moment. If dV is negative, like this scenario in here, and the pressure is always positive, then this number is going to be positive overall. So the energy, the work that we're going to do in this case is going to be a positive work. In other words, the value, the numerical value, the algebraic value will be a positive number, which means that this number has to go somewhere. So where in the world is it going to go? It's going to go to the internal energy of the gas. Actually, the gas will heat up. Okay, so that's basically what this means. So if you find the positive number, that means the energy of the system has gone up by this amount. Okay. Now, if the gas is actually expanding, namely its volume, let's say for example it was 1 liter, now it's a 1.5 liter. So the change in volume in this case is a positive number. So dV in this case is positive, which makes the entire work negative. So the system now must have lost energy in the form of this work that it's doing against the environment. So where did this energy come from? It must have come from its internal processes, internal system. So it's from the inside, from within. So that's what's basically what we're saying in here. In the absence of heat, what we're saying in here, the change in energy of the gas is simply the work that is done by the gas or against the gas. It's going to be negative if it's done by the gas. If it's done against the gas, it's going to be a positive. In other words, if it's done against the gas, we're going to add up to its energy. This is slightly different than what the book has done, because the book has a negative sign and removes the negative sign from here, and that's really not the standard convention. This is the standard convention. So in general, the change in energy of a gas is due to the added heat to it, or change in heat to it, and the work that is done against it or by it. So this is your first question, the first question for the discussion. Put this in your own words. This is called the first law of thermodynamics, by the way. So the first law can be stated, this is how I'm going to say it, and you guys can do it whichever way you like, is that to add energy, by the way, some textbooks, they use the word internal energy, and I used to say that, and sometime probably you will hear me say that, but Feynman had an objection on this terminology. He was saying internal energy as opposed to what? External energy? That doesn't mean anything. We don't care about what is external energy. Is it the entire universe or something else? So basically what we're talking about in here, the energy of the gas. So in order to add energy to a system, one way of doing it is add either heat or do work against it. Okay? Now, if you're saying, for example, oh, I added the two numbers and the sum was negative, well, what you did in this case was you removed heat, or you did or have the gas do work against the environment, or had both of them in such a way that the net number is negative, so you went down in energy. In other words, the temperature of the gas went down. Or you could have a situation where there is no change actually in the entire energy of the gas, by, for example, supplying heat to it, and at the same time the gas is expanding and doing work with the same amount, so that one of them is positive, the other one is negative, and they cancel each other. Or compress it, do work against it, and in the same time that gas is losing heat to the environment in such a way that again it has no change in its energy. So there is situations here. So this sum has to be an algebraic sum. So the way I define the first law, the way I express the first law, is basically it has to be algebraic. So you have to really take algebra into account in here. Meaning that this number could be at the end a negative number, and what you actually did was take or reduce the energy of the system. So that's basically what the point in here I'm trying to make in here. So this is your fast task. You're not going to put it in your own words. You need to know the first law, in other words. Okay, so that's good. So we have an idea now. Let's talk about this work in here, because it's an important concept that we had come up with. So the work in general, it's the integral from the initial position to the final position of this expression PdV. Remember, PV equal to nRT. So that's really something that we wrote up in here. But then you have to be careful with that one, because we are on a point on a PV diagram that has all kinds of things in it. So we know what P is, it's this point, this coordinate. We know what V is, it's the X coordinate. We know what T is, it's given by this expression. And we know now another thing, which is U, which is the internal energy of the gas. We don't really care for the exact number for it, just like the discussion that we had in Physics 1, namely the fact that the origin of the potential energy is really arbitrary. You can put it wherever you put. What matters is actually the difference in potential. Same thing happened in Physics 2 when we were doing the electrical potential. What matters is the difference in potential. So when your power company tells you that we're giving you 120 volts, what they mean with it is that the difference between the two ends of the plug is actually 120 volts. It doesn't mean that one of them is sitting at 0 and the other one is 120. It could be, if you like that convention, but then what matters is the difference. Same thing in here. Really, we don't care for the value of U. What we care about is if we're going to go from U, and there's some process from this point in here to this point in here, and there's some process that changes U. What matters in this case is delta U. Okay, and that's basically what the first law is talking about, is how to change delta U. Now, two things, I did not write them in the PV diagram, and namely Q and T, Q and W, and those are not state variables. I cannot say that this point has specific work or has specific heat. Heat depends on how we're going to depends on the process. Okay, it depends on the path. So remember, when you were doing again conservative and non-conservative forces, you ended up with conservative forces that are path independent, and those are state variables like the electrical potential or the gravitational potential. But friction, for example, was path dependent, so you could not have a value defined at specific point in space. Same thing in here. Heat and work are actually path dependent, so we cannot define them for a specific location. So let's take a process now. Let's talk about the processes. One process, isothermal process. This is a process that I know the temperature doesn't change. So we go from point to point on the same isothermal line. So meaning that the energy also doesn't change. So that's exactly what this means. That a process where the internal energy of the gas stays the same, because the temperature is the same. So how this looks like on a PV diagram. So again, we have the volume, we have the pressure, and this is how that, because this function is simply PV equal to nRT, P equal to nRT over V. So this function is a 1 over x function, because n is fixed, r is fixed, t is fixed. So this is just how it goes. So basically this is how the line would look like. So we were at some point in here, defined by position V1, and pressure P1. I mean x coordinate. Now we're going to end up in a different location, volume V2 and pressure P2. Okay, so we increased the gas basically size and from volume V1 to volume V2, and at the same time we lowered its pressure, so we decompressed it. So we want to know what W is, what the work is. So the work is going to be simply equal to minus the integral from V1 to V2 of PdV, and I know what, in this scenario, what P is, so it's going to be, because nRT are constants, divided by V dV. nRT comes out of the integral, and we'll be left with the integral of dV over V, which is just the natural log. So in this case, the work is going to simply equal to minus nRT ln of V2 over V1, or nRT ln of V1 over V2. I just moved the negative sign on the other side. Obviously, this whole thing is negative. So when the gas is expanding, it's doing work against the environment. So it's losing energy in the form of work. That's why the number is negative. Losing is negative. So in this case, but the energy overall is not changing. Remember, delta U is 0, which is Q plus W is 0. This is negative, so this must be positive. So Q, which is must be equal to minus W, is equal to minus times minus, which is positive nRT ln of V2 over V1. Indeed, this is exactly what the heat is going to be in this situation. So the system is getting heat from the hot source, because it's sitting in contact with a hot source T in here. So it's getting heat and it's doing work. And the heat that is getting is equal to exactly in absolute value, in algebraic, in magnitude only, to W, but they are opposite in sign. If I do the process backward, if I compress the gas basically, then in this situation W will be positive and Q will be dumped into that heat source. Okay, sometimes called the heat reservoir. Okay, anyway, so this is an isothermal process. We understand it. We can find all of the values that we will need for this particular situation. Another process of interest to us in here is a process that is where actually the volume is constant. So we're going to talk about the isochoric process. So the isochoric process is where there is no change in volume. So if there is no change in volume, then in this case W is equal to 0. Remember, the work, if we go from small steps, is equal to minus PdV. So in this case is going to simply equal to 0, because there is no dV in this case. So W is equal to 0. That's an important concept in here, which means that all the change in the energy is coming just from the heat that is added to it. So that's the first scenario that we talked about. Actually, we fix the sides, we screw them in place. Basically, we use glue there to fix them in place so the piston doesn't go up and down, and then we turn the heat on, and the energy of the gas starts to increase. That's what you do when you cook, for example, with a pressure cooker. So basically, that's one way of adding heat to the gas, and the temperature will rise in this situation. How much heat will go? I'm going to define a specific value now to find that one in here. So what I'm going to say in here, by definition, the molar specific heat is at constant volume, because this process is isochoric process. Okay, this process is at constant volume. So at constant volume, is going to be CV, such that the amount of heat in this case is proportional to the change in temperature, NCV delta T. So in this case, the definition, if you wish, is the molar specific heat has to do exactly with the number. Of course, this is for 1 mole multiplied by the number of moles times the change in temperature. So that's basically the process, how we define a molar specific heat. It's immediately equal to U in this case, the change in the energy now. Okay. Remember, for a gas, we defined that for at least a monoatomic gas, we found that the energy of the gas is equal to 3/2 RT. For a diatomic gas, we find it to be 5/2 of RT. So those quantities are actually the amount of change in energy. So that is actually CV. So du in general is going to be NCV dt. And if we go back into the expression that we did from the previous chapter, we will find that CV is equal to 3/2 of an R for a monoatomic gas, mono. For a diatomic gas, CV will be equal to 5/2 of an R, and this is a diatomic gas. And for a polyatomic gas, is going to be a number that you can find later on. Okay, so this is from the previous chapter. So that's basically the expression. This expression is true all the time. Always. In particular, if we go back to the previous case, if we go back to the previous case, let me pause quickly in here. You guessed it. I'm sorry about that. Okay. So that's a typo in here. Yeah, okay, anyway, so the point being in here is that it's always true, this expression in here. So du is equal to NCV dt. So if we go back to the previous case where dt was equal to 0, namely an isothermal process, that recovers du equal to 0. That's important, that's related to the previous idea. So that is one way of finding the molar specific heat, basically at constant volume, CV. Okay, another process of interest to us. So from now on, basically a gas, you can find its specific heat. So if they tell you it's a mono, you know exactly how much CV is. If they tell you it's a diatomic gas, you know what it is. Otherwise, they will give you the value for CV. Okay, or they will ask you to find it, actually part of the problem. If the process is an isochoric process, so you know delta U is just equal to the heat. There is no W. W is equal to 0. Another process of interest, so there's third process if you're keeping track of them. This process is the isobaric process. Okay. In an isobaric process, there is no change in pressure. So this is constant pressure. Let me draw something in here so that you guys see it exactly what I mean by an isochoric process first. So at a fixed volume, there is no change. So if you could go from pressure P1, for example, to pressure P2, we're compressing the gas in here at constant volume, just like what we were doing earlier. So basically, we're moving we're fixing the volume. So the volume is not changing, so like a pressure cooker, but in this case, we're increasing the temperature or something like that. So the gas now energy is increasing, so there is higher and higher pressure. That's why it's called the pressure cooker. Okay. So we go from a temperature T1 to a temperature T2, where T2 obviously is higher in this case. So we're compressing the gas. Okay, so that's one way of doing it. So that's the process that you can think of. Okay, in an isobaric process, now just to keep up with the drawings, this is how the isobaric process would look like. So this is the volume, this is the pressure. And now we are at constant pressure. For example, we could expand from volume V1 to volume V2. Obviously, the gas is expanding. In this case, it's doing work against the environment. So W is not equal to 0 now. And so this is the pressure that is fixed. And now we want to find what that work is. So it's simple in this case. W is equal to minus the integral from volume V1 to volume V2 of PdV, I'm sorry, where P is constant now. P comes out of the integral. It's minus P, the integral of V1, V2 of dV, which is simply equal to the difference of the two volumes times the pressure. So that's how much work there is to it. So in this case, we know how much work. It's minus P times the change in volume. Obviously, this number for this case, for this example, is negative because the change in volume is increasing, which means that the work in this case is negative because the gas is doing work against the environment, which means now that energy must come from somewhere. Since it's negative, the system is losing it. So in this case, the system is losing that much energy. But the energy overall, it's still delta U is still Q plus W. Okay, so there is a change in the energy in this case due to both. So how much is Q now? By definition again, the molar specific heat at constant, it's no longer volume, but now constant pressure. Cp is defined in such a way that the heat in this situation is equal to Ncp delta T. So in other words, in my expansion in here, I must have gone from some sort of an initial isothermal T1 to a final isothermal T2 in such a way that is heat exchange. So I'm getting heat in here, and that's how much heat I'm getting because I'm going to a higher temperature now. So I'm heating up the gas, but in the same time I'm doing work against the environment, so there is a change in the energy of the system, and that's how much it is. So Cp now is the molar specific heat at constant pressure. That's why I have to multiply it by N, because it's by definition molar, that means per unit mole. Okay, times the difference in temperature. So again, for a specific gas, we need to know what its Cp is. It turns out Cp and Cv there is a one-to-one relationship between one another. So we need to find that, because I told you that you can find Cv, or it's going to be given to you. So how in the world we're going to know what Cp is? Well, for Cp, we need to do some work. Okay, let's go back to PV equal to nRT. PV equal to nRT. Well, we know that the pressure is constant, so the only way for this expression for the temperature to change is through the volume. That means nR dt is equal to PV. PdV. So that's basically how much it is. So in other words, the work is going to be minus, the change in work in this situation is going to be minus nR dt. Because if I multiply by a negative number, that's how much work there is too. However, the energy is equal to the amount of heat added. I'm taking a finite amount of time now, finite amounts of displacements now. That's why I'm using dq plus dw. Okay. Well, dq by definition is nc dt. That's how we define the molar specific heat, by changing it from one small temperature from T to T plus dt. And plus the work in this case is minus nR dt. Whereas I argued earlier that this is always ncv dt. The change in the energy of the gas is always equal to the number of moles times the molar specific heat at constant volume times the change in temperature. So this is the expression that we ended up with then. Ncv dt is equal to ncp dt minus nR dt. Obviously the dt and the dt and the dt cancel, so is the n and the n and the n, and we end up with a relationship between Cp and Cv which looks like this. Usually it's written as Cp is equal to Cv plus R. So in other words, if we know what Cv is, we know actually what Cp is too. So there is only one parameter you need to know when you're solving a problem, Cv. So if you want to know what Cp is, all you have to do is add to it an R and you're done. Okay? So that's kind of important. The relationship is extremely important. As a matter of fact, there is another quantity that I'm going to define, which is part of your lab, by the way, which is doing this. Gamma, by definition, is equal to Cp over Cv. So if I write that expression, which is Cv plus R over Cv, then this expression is simply 1 plus R over Cv. Again, if I know gamma, and that's part of the lab that we'll be doing, is finding gamma, then I know what Cv is, because R is just a constant. And if I know what Cv is, I know what Cp is. So that's basically what this whole thing is. So if there is a lab for us to determine gamma, which is the gas constant, by the way, which is the ratio of the specific heat over the specific heat at constant pressure, the molar specific heat at constant pressure over the molar specific heat at constant volume. So that's basically the characteristic of gases. Okay, so let's find what this Cp first of all is for a monoatomic gas. I know it's 1 plus R over, so this is a monoatomic gas. Cv, I just argued it's 3/2 of an R, cancel the R's, and move the 2 to the up, so it's going to be 1 2/3, or 1.667. So This is not Cp, I'm sorry, this is gamma. I'm using this expression. Cp, if you like, is simply equal to Cv plus R, and Cv is 3/2 of an R plus R, so it's going to be 5/2 of an R. Okay? So we can find what Cp is. That's for a monoatomic gas. For a diatomic gas, let's find what Cp first is. It's Cv. Remember, Cv for is 5/2 of an R. That's how much the Cv is for a diatomic gas. Add to it R, and the common denominator is 2, so it's 7/2R. So that's the Cp, and gamma in this situation is going to be 7/2 of an R divided by 5/2 of an R. Cancel the R's and the halves, and it's going to be 1.4. So for a diatomic gas, we know what it is. For polyatomic gas, you'll have to involve other degrees of freedom, and it's going to be different, okay? It's going to be slightly less than 1.4. It's 1.3, 1.33, or something like that. So that's for triatomic gases. Anyway, we can find what this gamma is, we can find what this Cp is if we know what gas it is, or vice versa, or if we find what gamma is, we know exactly what type of gas we're dealing with. And that's part of the problems we'll be discussing today. There are problems 38, 39, and problem 60. So that's the problems we're going to be discussing. Anyway, so that's the interesting stuff that we have in here. The fourth process that we're going to discuss in here is the process called an adiabatic process. What an adiabatic process is by definition there is no heat exchange. Okay, you wrap your gas in a blanket if you wish, or you insulate it somehow so that it doesn't gain heat or lose heat. So that's the word you'll be looking for in problem solving, insulation. If you find that, that means the gas is going through an adiabatic process. So how does this look like on a PV diagram? On a PV diagram, this is the volume, this is the pressure. So we have some sort of an isothermal. Let's call this one T1, for example. And we have a higher temperature. Let's call it, for example, T2. The gas, let's say, for example, started at a higher temperature in volume V1 and pressure, let's call it P1, and ended up in a different pressure and different volume and different temperature. So this is volume V2, pressure P2, and temperature, oh man, I gave the wrong symbols. Okay, so let's put T1 in here and T2 in here just to be consistent, okay? Because everything 1 has to do with the initial position and anything 2 has to do with the final position. Anyway, so this is the process we're talking about, this process in here, going from the initial points, coordinates P1, V1, or V1, P1, to the final point, which is coordinates V2, P2. Okay, and this is Q equal to 0, or the so-called adiabatic process. Obviously, since Q is equal to 0, then delta U is just equal to the work in this case. Having the gas expanding this way, that means doing work against the environment. That means W is negative. That means delta U is negative, and sure enough, the temperature went down from the higher temperature to the lower temperature. Okay, so everything is consistent. You really have to pay attention to all of these things. So we need to find W. If we find W, we find delta U. We know what Q is equal to 0 in an adiabatic process. So the point in here is trying to find this value from volume V1 to volume V2 of P dV. Okay, but in order to do that, I really need to find what this function P as a function of V is. I need to find what P as a function of V is. If I know that, then I can plug it in here. I don't know it. Don't tell me it's PV equal to nRT. I mean, this is true for every single point of equilibrium on the PV diagram. So for this relation to be true, by the way, we need to be in thermal equilibrium. So it's true in everywhere in here, but it's not a description because T is changing too. So everything is changing in this expression. So I cannot plug in PV equal to nRT because T cannot come out of the integral. This is not an isothermal process. So this is not going to help me now. So I need to find what this function is first. Okay. So let's do that. So we need to find how P and V are related to one another. So let's go back to the expression that we started. PV equal to nRT. That's correct. That's still the expression that we're going to be dealing with. But now, P is changing, V is changing, T is changing. So if I use a differential form on this expression, I find that dP times V plus P times dV is equal to nR dt. That's good. We know that. Okay. whereas the change in the energy in this situation is equal to minus PdV. Okay, which is equal to NCV dt. That we argued from the first point in here. It's always change in energy, it's NCV dt, whenever there is a change in temperature. Okay, but in this situation there is no heat change, so dq is equal to 0 because the process is by definition adiabatic. So the first part in here is the first law. The second part in here is the fact that always when there is a change in temperature, there is a change in energy. So I know what n times dt is. N times dt from the second expression here gives me n times dt is simply equal to minus pdv over cv. So I'm going to plug it back into this expression, and I will have eliminated dt out of it completely. And I will be dealing with just p and v. And that's exactly what I'm hoping to find, is how p and v are related to one another. The only problem is we're going to have an integral form. So that's all. So the first side in here, I'm not going to tinker, and I'm not going to mess around with it. So I'm going to leave it as is. So it says v dp plus p dv is equal to nRT. And nRT now is equal to minus pdv over cv times r. So I need to multiply that by r. So it's minus r over cv times p dv. That's all. So this is the expression I ended up with. Since I have pdv in here and I have pdv in here, I'm going to move them to the same side and have at the end v dp plus 1 plus r over cv times pdv equals to 0. Before I integrate this expression, I'm going to divide by pv. So I'm going to divide the entire expression by PV. In doing so, this V and this V in the first term cancel. This P and this P in the second term cancel. So this is what I'm going to end up with. dP over P in the first one plus 1 plus R over CV times dV over V, because the P cancels but the V stays, is equal to 0. Before I continue any further, I know what this term 1 plus R over CV is. 1 plus R over CV is way up here when we were defining gamma. It's actually gamma itself, 1 plus R over CV. So I'm going to write this expression in terms of gamma then. So what we ended up with is dP over P plus gamma times dV over V is equal to 0. If I integrate this expression, the integral of 0, first of all, is going to be a constant. So the second side is going to be constant. And the first side is the integral of the dP over P. That's ln of P. And the plus gamma times ln of V. Okay? I'm going to combine these ln's in one expression. So what I'm going to do in here, I'm going to say this is ln of P plus ln of V to the power gamma. It's the same thing. Okay, equal to a constant. Now ln plus ln, that's ln of the product. So this is ln of P times V to the power gamma is equal to a constant. And if I take the exponential of both sides, I have PV to the power gamma equal to constant, which is just exponential of a constant, which is just another constant. So if you're curious about what this constant is equal to, remember this is the expression now for the adiabatic. This is the expression for this line in here. This is the expression for this line itself. This line has the form PV to the power gamma. That's exactly what this is. Since this point is part of it, so this is equal to a constant, and that constant and that point, it's P1 V1 to the power gamma. Or, since this point also is part of it too, is equal to P2 V2 to the power gamma. So I know exactly what that constant now is. Okay, either from the starting point or the ending point, I can express it actually in terms of the temperature too. As a matter of fact, the entire expression can be changed now to be expressed in terms of the temperature. So this is basically what this expression then says, what the line of the curve is. So this constant is P1 V1 to the power gamma, or P2 V2 to the power gamma. It's the same number, since this is the expression true for all points on that diagram, on that line, I'm sorry. So this is the expression for the PV diagram. Now let's finish what we started with. We need to find what the work actually is from V1 to V2. Now I know what this P dV is. P from this expression is equal to that constant. Let's call it P1 V1 to the power gamma divided by V to the power gamma. So this expression then becomes minus P1 V1 to the power gamma, which is constant. The integral from V1 to V2 of V to the power negative gamma dV. Note that gamma is always greater than 1. Remember, gamma is equal to 1 plus R over CV, and all of these quantities are positive, so it's always greater than 1. So I can do this integration in one step, basically. All we have to do is add 1 and divide by the new exponent. So the work in this case is going to be equal to minus P1 V1 to the power gamma divided by negative gamma plus 1, and then I have V to the negative gamma plus 1. All I did was I'm integrating this V to the negative gamma, knowing that that number can never be equal to 1, so we're safe, at least in terms of the integration between the points V1 and V2. So we have found the work, and now we can find the entire expression for the energy and so on and so forth, and I leave that to you guys to finish it, because you can express it in multiple ways. Second question of the day actually has to do with this PV to the power gamma, which is constant. Ignore the constant, what it is. Sometimes it's written as K now, okay, or K1 actually, I'm sorry. Another way of looking at this expression now, since PV equal to nRT is true all the time in this process, okay, what I can do in here is I can find P from this expression and sub it back into this expression, okay, and move the constant. So let's do it quickly in here. So P, if I multiply it, it's going to be nRT times V to the power gamma, and I have a V in the denominator, so it's going to be V to the power gamma minus 1 equals to K1. So in other words, in a TV diagram, not a PV diagram, I will have the expression T times V to the power gamma minus 1 equals to K2, whereas K2 is simply K1 divided by NR, okay? So that's basically how where K2 is another constant, because K1 was a constant and number of moles is constant, R is a constant, so it's another constant. So this is basically part of the question for the lab. So I need you to finish this one, because you're supposed to use the same expression, PV to the, Control Z, PV equal to nRT, and eliminate in that process the volume now. So we're going to put the volume in here in terms of P and T, and then find a new constant in here that relates to so this is in a TV diagram actually how the expression looks like. We found that in a PV diagram, this is how in a PV diagram would look like. So the question that I hope that you guys is not hard for you to do, any TP diagram, how this would look like. In a TP diagram, how it looks like. So basically use this expression to get rid of V. V equals to nRT over P, and sub it in this expression, and now you will have an expression that has P and T in it, and with the new constant, okay? And that's basically the second question of the day. So this is the entire chapter. I know it was a little bit long, but I'm hoping that you guys have understanding. Join me for the second part where we talk about the 3 problems, 38, 39, and 60 from this chapter. Thank you.